welcome to Rational Science. Let me do a couple of things here because I've had problems with the sound, and I bought a lollipop, but it didn't do the job. I think there are problems with my computer, and until I get back to Frankfurt, I'm on the road, I won't be able to fix it, I suppose. So all I can do is ask you to turn your volume up as best as you can. Okay, because this is the best sound I can give you. I've had all kinds of problems with the sound. Let me know if you are completely deaf, if you can't hear anything that I say. I'm a little worried about that, but otherwise just turn your sound up. That's all I can do, okay? Anyways, let's see if I can do a couple of things here. Give me a second. That might help. Okay. I hope it might help. Okay, got that. Okay, once again, let me know. Okay, let me know if you can hear me. I've had all kinds of problems, and so thank you. Thank you, guys. Thank you. Okay, we're going to talk a little bit about particles today. What are particles? Well, forget about particles. We have some special types of particles that will blow you away if you're not familiar with them, right? And I'm going to begin a little bit as an introduction to that with the stuff we talked about the other day so that we move into the particles. But first, let's find out what particles that don't exist, that have been invented by mathematics, by equations. Okay, they've been invented. There's no certification, no, as they call it, no discovery of these particles. The way they discover them is through equations, through some kind of mathematical, footwork, and but they haven't seen them, they haven't touched them. There's no verification of these particles. It's just math that has been turned into fact. That's all. And so let's review that. I covered that last week, but I'm just going to go through that as an introduction to the second part, which is the particle world that these people created. Okay, the first one. Now, we have no such thing as dark matter particles. You say, Bill, how can that be? They proved them. In fact, in 2008, they gave the Nobel Prize to the people who in 1998 discovered the dark matter particles. They say they exist. We just have to find them now. So how can they discover them if they have to still search for them or tell the astronomers to look for them? Well, that's where the trick is, So here it is. What is this dark matter stuff? And I want you to understand this. This is very important to understand, okay? It's very important. You have, you don't have to know all the details, but you have velocity squared there at the top, right? That v squared, that's velocity squared. You got the gravitational constant g and the mass, the center of mass, essentially, of the thing in question, in this case, the galaxy, right? Okay, so we have that. That's why that's a big M. So what's the issue? The issue is that radius of a star, how far it is from the center of this whole shebang, right? The radius, the bigger it is, as you can see at the bottom, the smaller the velocity, because radius is in the denominator, okay? So they're inversely proportional. The bigger the radius, the smaller the velocity. Very simple. You see it with Pluto. The bigger the radius, the smaller the velocity. Mercury is close to the sun. It's got a shorter radius, right? And it goes fast. Pluto is way up there in the middle of nowhere, and it goes very slow. Very simple to understand. You can prove it to yourself by rolling a ball around your head or a rock around your head or at the end of a string. The longer you make the string, the slower the thing will go around you. Very simple. That's not the case with stars at the edge of a galaxy. It's called the galaxy rotation problem. And so what they had to do, they had to put a fudge factor. It's called science, right? fudge factor called mass, as you see at the bottom, okay, to compensate for the extra radius. So if radius bloats, if it gets big, if the star is farther away, you have to compensate for that. In fact, overcompensate in reality, put more mass in there so that the velocity is faster. Okay, that's what they did. So those red dots that you see, that's the dark matter that they discovered. I guess you can call it that. They discovered this dark matter, this dark mass, and now they tell the astronomers to go look for it. And for their disadvantage, it's conveniently invisible, translucent. You can see the stars in the background right through them. It ain't there. It has no charge. Okay, all it has is mass, and it's just invisible mass. Yeah, it's what is known as a fudge factor in science, right? They had to put that mass in there in order to get the stars on the outskirts to travel faster or as fast as the ones on the inside, and that's the whole problem. The question is whether this thingy called dark matter exists at all, and the answer is no. These folks, in order to explain why the stars on the outside go faster or faster than the ones on the inside, they put that mass. But maybe this is not a massive phenomenon. Maybe it's got nothing to do with gravity. And that's our take here. We have a different explanation for that, but we're not going to cover that today. But yes, we do have a rational explanation for dark matter, the so-called dark matter phenomenon. Okay, here we have another invention of math. It's called the quarks. Okay, are there quarks? Are there gluons out there? What's a quark? Well, they have these 3 quarks, allegedly 3 quarks. We're going to find out today that it ain't 3 quarks. It's a little more than 3 quarks. It's infinite quarks, okay, but we'll get to that later. But they have 3 quarks inside a neutron or a proton. They're held together by these so-called particles called gluons, which carry the strong force, okay? They keep them together somehow. And the question is whether quarks exist. How did they find them? How did they discover them? The word they use is discover. We discovered. And when you discovered, you get a Nobel, right? And how did they discover them? Well, again, a mathematical trick, nothing but. Okay, here it is. Okay, showed this the other day. You have these charges, and we'll call them visas and MasterCards. So you have a Visa and you have a MasterCard, and in them you have $66 in each of them, right? So you have $133 between the 2 of them. Turns out you have a negative charge, which is your MasterCard, and that's a negative 33 that you got there. So if you take 133 minus 33, well, you get 100, meaning 1. That means that you have the unit charge, which is 1.6 times 10 to the minus 19 coulombs. And that's why the proton has a positive charge. Now you know. Okay, you have 2/3 plus 2/3, that's 4/3. Minus 1/3 of your negative MasterCard there, that gives you 3/3, meaning 1. That's the charge on the proton. Why did they have to invent this system? Well, there you have it. The neutron has no charge whatsoever. So how can you explain with charges that neutron has no charge? Well, very, very simple. So now you take the 2/3 charge of your Visa. You have $66 in there, right? But you owe $33 in each of your 2 MasterCards, your down quarks, or whatever you want to call them, okay? So you have 2/3 minus 1/3 minus 1/3. You have 0 charge. That's why the neutron has 0 charge. See how easy it was? It's just a mathematical trick. There are no such things as quarks. There are no such things as gluons. They haven't proven them to exist. It's just a mathematical contraption. It's just math to show why one has charge and converts to the other, which has no charge, and vice versa, which is called the decay, beta decay. Okay? So neither dark matter, neither neutron, quarks, no such things as them proven to exist. These are just mathematical nonsense. That's what I call it. It's just garbage. That's all it is. It's it's got nothing to do with physics. It only has to do with math. Okay. Okay. Now, just in case we have no gluons either. Okay. Here we have the gluons. Okay. It says in the Wikipedia, how do gluons pull quarks together? Okay, yeah, how do they do this? And you can see there these bed springs that are between the balls at the top. Okay, those are the gluons. Okay, and so here you have gluons which carry the strong nuclear force, bind quarks together by how? Constantly exchanging between them, creating a strong color force field that holds them together. Well, they haven't explained anything with that. I mean, what is a color force field? You know, they say it creates this field. Okay, so what's a field? Well, it's a bunch of numbers. That's what it is. So we don't have an explanation of physical interpretation for the gluons. But they illustrate them as bed springs there. Okay, in fact, here, for the first time in your life, you're going to see the quantum gluons. I want you to see this. You saw it here first. I want you to spread this around the world. Okay, you saw it in bgaede's Rational Science Group, and here it is. That's what a gluon looks like. Okay, it's a bed spring. Okay, so if anyone asks you, now you know. You can illustrate it for them and say, hey, I know what a gluon looks like. It looks like a bed spring, because that's what they illustrate. Okay, what else can they do? Okay, so what does the Wikipedia say? Quarks interact with each other by emitting and absorbing gluons. Okay, well, so if you absorb a particle, how does that bring you together to another particle? Okay, so again, you cannot explain attraction by throwing stones at each other. That's where the problem is. The mechanism is irrational. And the way they do it in math, very simple. They just put a negative sign in, and they got a negative field or a negative mass or whatever, negative energy, negative force. So all they have to do is put a negative sign in front. They're done in math. Then they tell the physicists, well, go look for it, right? And yeah, it's very hard to look for a negative sign in physics. It says this exchange of gluons creates a strong color force field that binds quarks together. That doesn't tell me anything. What's a color force field? Well, it's just it's just a number. That's it. And then the question also is, if you have all these quarks, what prevents the quarks from coming together? And again, it says the strong force pulls, but what repels to equal out? Because why don't these quarks collide against each other if they're brought together by these gluons? Well, they tell you there at the stack exchange, bastion of so-called mathematical physics, right? So as the strong force does pull quarks together, but it also gets weaker as the quarks get closer. In other words, it acts sort of like a what? A spring, wouldn't you know it? In a phenomenon known as asymptotic freedom. Okay, whatever that is. Anyways, the issue there, you can see how you need energy required to pull them apart is ever greater, but as they come together, the force decreases. And that's why the quarks don't collide against each other. That's the explanation for this. So they have a double whammy. On the one hand, they can explain why, a triple whammy really, why the quarks don't crash against each other, why they don't fly apart, because the farther they try to come apart, the stronger the force. And then it also explains why, why quarks, two up quarks for the proton and one down quark gives them a positive charge, and for the neutron, when you have it in reverse, two negative charges, third charges, they had to invent a third of a charge, right? Against a positive two-thirds, cancels out, and that's why the neutron has no charge. And beta decay assures that one can convert into the other every 15 minutes and vice versa. There you have it. That's in a nutshell the particle world of quantum. Take it or leave it. Those are the explanations. It's all math. None of it has to do with physics or with the real world. Okay, here we had the other thing that we touched upon the other day was neutrinos, and here you have them. The neutrino was postulated. Why? Because a particle is sometimes taking a varying fraction of energy during beta decay. The neutron could decay to a proton, electron, and a smaller neutral particle, now called what? An electron antineutrino. And there you see the little symbols they give you, the little V sub E, that's the antineutrino. It's a positive one. And then there are three discrete neutrino masses, the smallest of which could be 0. So we have a neutrino that can be 0 mass And they say the wording that they use to really get you is that it interacts very weakly with matter. In other words, the neutrinos run right through you, through every atom in your body, and nobody questions that. How can a neutrino run through, which is a piece of matter because it's a particle, how can it run through your body, which is also made out of matter? And the answer is all of this is just math. That's all it is. So you have a number 5, that's what's running through your body, if you can understand it. But the good part is on the right side here. The neutrino possesses a mass. Listen to this. Possesses a mass, right? We're talking about mass. What do we measure mass in? Kilograms, was it? Of at least 0.07 electron volts, a millionth of an electron mass. What do you mean an electron volt? I thought mass was measured in kilograms. So they say there at the bottom, particle mass is expressed in E, energy, right, over c squared, or what? Electron volts over E squared. That's mass, and you're saying, well, I thought that was energy. Well, there you see the answer. Units based on equivalence of mass and energy. So they always talk about mass when they really mean energy, because according to Einstein, energy is equal to mass times velocity of light squared. Okay, so it's a mathematical contraption again. And have they ever found the neutrino mass? Well, it says evidence for the neutrino mass was provided by demonstrating that neutrinos can oscillate from one type or flavor into another. You know, electron, muon, tau, neutrinos, etc., as they travel through space and matter. Travel through matter. Did you hear that? Let me say it again. Travel through matter. So people ask you, how does a rope go through a rope? Well, there you have matter going through matter. Why don't you question that? Okay? Oscillation can occur only if the neutrino possessed mass. If it doesn't possess mass, then we have a problem with oscillation. But as you can see on the left side, it says the smallest of which could be 0. So we have some of these with 0 mass, and still they talk about oscillation, and they have all these contradictions, and they just live with them. Okay? And then they tell the mathematicians, fix the problem, you know. So they give it to the advanced studies there in Princeton, and these people break their brains and see how they're going to fix this problem mathematically. Current limits in neutrino mass is, and there you see, okay, so they have all these values for neutrinos, and you know they have all these answers. They have an answer for everything. The neutrino has mass and also doesn't have mass. It's 0 mass. And it needs mass for oscillation. Never mind, if it doesn't have mass, it'll oscillate anyways. And can it go through a particle? Yeah, it can go through a particle, through your body, through a proton or a neutron or an atom or whatever. It goes right through matter. Or it acts weakly with matter. That's how they put it. That's the way they get away with it. It's weakly interacting particle, or WIMPs, or whatever they call them. Okay? Okay, so all this nonsense is what they feed the public. Okay, they're trying to translate their math into physics so that the people out there can understand it qualitatively, more or less. Like, you know, everybody understands more or less. If you say, well, what is gravity? Well, you know, here we have gravity, right? You have a thing and it falls down, right? We all understand that. And I don't need any math to try to figure out what the mechanism of that is, what the cause of that is. We don't need math for that. But these people give you math and they translate it into qualitative physics, right? And they can't. And so they have to invent all these words, these fancy words and these fancy mechanisms where they introduce magic, supernaturalness, right? That's what they introduce in there. And that's what they feed the public. And people say, well, we wouldn't have all this technology if it weren't for that all these guys are correct. That's the logic out there. You know, you wouldn't have a computer build if quantum were wrong. That's the answer they give you. And no, quantum or computers do not prove that a particle can be at two places at once, or that a neutrino can go right through the wall. Okay, it doesn't prove that. That's an assumption. That's an irrational theory that they have, and they just tell you swallow it because otherwise you wouldn't have a computer. Okay, they could have used angels and ghosts and spirits, and you would have believed it anyways. Oh, computers wouldn't work if spirits were not around. You know, yeah, that's what it is. Okay, so here we have the traces, and this is where they get all this nonsense from. You've seen that last week. Here it is. All these traces. And this is what they see in their accelerators. They have a bubble chamber chamber filled with gas. And when they make an image of a so-called collision of particles, this is what they get. They get all these little curlicues. Okay, and so the question is, are we staring at curlicues, traces of particles, of discrete particles that are running around at greater than the speed of light, because in order to turn those corners at that speed and be able to make a snapshot of that or image it somehow with a computer, I don't know, that's kind of weird. You would have to really strain yourself to think that these are the curlicue, especially the very well-rounded ones, are traces of particles. How did they do that in gazillions of a second? I mean, here you have the one I showed the other day, the electron traces, okay? You can see that. The electron spirals 36 times in a magnetic field. How did they take a picture of this motion? Okay, you're talking about a movie that they took a snapshot of. In other words, you got many frames of the film right there, okay? And the question is this, does this make any sense? That you can take a picture, a snapshot, right, of a trace, such a curved trace, right? And that's what all these are. They claim that these are particles that are tracing very circular paths, and that they took pictures of them. In other words, they imaged them with a computer program that already assumes that they're talking about a little particle that's running around in circles. Okay, so if you concede the assumption, well, yeah, then maybe you can say, yeah, those are traces of particles. But if what they're staring at are not little discrete particles that are running around in circles, then all this is BS. I think that's a good word for it. And here, this is, remember the suppositron, Anderson suppositron? I like to show that because he called it the positron, and I call it the suppositron, because he made an assumption that he was looking at a trace of a particle, which is here, okay? And again, he said, look, as you can see in the plate on the left there, the big one, okay, the little scratch mark there is going towards the left. From your point of view, it's going towards the left. And they sent this through a magnetic field, right? And they said, well, if it were an electron, it would have gone to the right. But since it went to the left, they said, this is a positive electron, and that's why they named it the positron instead of the electron, right? The negatron, I guess you would call it. And I call it the suppositron because he made an assumption, a supposition, that this was a little tiny particle. And again, the question is whether you can produce such a quick trace, such a curve in such a little space, in such little time. Okay, and a second problem with that is that this was a jumping beam because it didn't leave a complete complete trace. What it was is some places are missing the little pothole. And so the question is this a bean that jumped up and down, like a jumping bean, up and down and made the little potholes? Because there was no continuous trough, okay? So that's another issue. And so how do we explain it? Well, we give it a whack with a thread from our theory, okay? We're saying that if you make the assumption that light consists of a rope, and these the two threads of the rope, or one of them at least, comes out of the rope and swings around during a magnetic phenomenon, then you can imagine how that could hit the gas in the chamber or whatever and create this curved image. Okay, so maybe what these people are doing is, instead of looking at a trace of a particle, they're thinking of something that gave it a whack, right? Just one whack, and made that curve like you would hit with your curved rope. You hit the paint on the wall, you would leave a curve. That's what we think is happening here. And here, let me illustrate that for you. Here you have two kids, and they're jumping rope, and you can see how one is pulling on the other one because they're going the same direction and they're very close to each other. So in this case, they're going counterclockwise, the ropes, and one is pulling on the other. And that's the mechanism we have for magnetism, okay? So keep that in mind. So here we have the construction of the of our atom, okay? Okay, I got to give this introduction so that you understand the whole theory. Here's the our atom. We have the electric thread, magnetic thread. Those are arbitrary just to keep with convention. And one goes around and makes the electron shell or membrane. It's a ball that encapsulates the proton star in the center. Okay, you can see all the ropes converging on our atom, and what they do as soon as they get to the electron shell, they fork out. One thread goes straight to the center of the atom and out the other end, and the other one goes around and encapsulates all these threads. Okay, that's our model. Okay, so that's what we're saying is the atom. But this is a static version of the atom. Okay, this is just a static version. Let's look at now how it really is. Let's go slowly, going one step at a time. Here it is. You have two threads and they're turning around, okay? Now we can all understand this, I think. You know, you just imagine two threads just rolling around each other. Okay, so far so good. And so our atom is like a ball of yarn, really. Okay, let me show this. Here it is, like a ball of yarn. Okay, here it is. That's what our atom looks like. But those, that surface is not static. It's moving around the atom. So they're all twirling and moving around at great speeds, right, around the atom. And they have all the ropes from everywhere in the universe converging upon our atom. And yes, the ropes go through the ropes. Okay, so under the rope model, we have no problem in understanding what quantum has been saying for so many years, that things go through things. And people have trouble with that because they say, hold it, the rope converges on the atom and the atom twirls and goes right through the rope. Exactly. That's what we're saying, okay? So I want to make sure that's clear, okay? So don't ask the question again. Please answer the question for quantum mechanics. How do neutrinos go through atoms? That's what you got to answer. When you answer that question, I'll answer this one, okay? Okay, so that's our atom. You have a ball of yarn encapsulating a proton star, as we call it, okay? And you have all the ropes converging upon it. But again, that ball of yarn is not static. The surface of the ball of yarn, which we call the electron shell, electron membrane, is not a static thing. It's moving around at great speeds all around the atom, okay? So let's keep that in mind. We're just trying to explain. You don't have to believe in any of this, okay? We're not asking you to believe. We're just trying to tell you what we're proposing. That's it. This is our theory. Okay, so here we have, again, an atom, and it's made like that. I hope you can imagine it. What we're saying is all these threads are moving around the atom, the surface of the atom at great speeds, okay? But what happens? Every now and then, what you have is a thread comes out. Maybe it's more than one thread, but I always do it with one thread. And it's important for you to understand that thread because with that, you're going to produce ionization. You know, the ionization in quantum mechanics is a little bead that goes around the atom and just flies out of the atom and comes back whenever it's a positive ionization or whatever, right? Or a negative one when it leaves, right? And what we're saying is nothing leaves. There's no little ball, little bead that leaves the atom or comes to the atom. What you have is a thread, or maybe it's more than one thread. This is something we have to look at later on, but at least one thread comes out and it swings around the atom. So the atom really looks more or less like this, okay? And so you have the atom there, and what I'm illustrating that there is that one of the threads extends beyond the surface of the electron shell and just swings around. Why do we need this under the rope model? Okay, and let me show you why. Okay, so that you can criticize it later, but please understand it first. Okay, so here it is. We have what is known as an ionic bond. Okay, here we have two atoms, or really two orbitals. One is the orbital and the other was a p orbital, different atoms, right? And what you have is the s orbital will merge with the p orbital, okay? And you can see how they're twirling around. In this case, they're both twirling clockwise, okay? What they call positive and negative. And what's the issue there? You have this high energy region, as they call it. Why? Yeah, because you have a lot of activity there, okay? And so what happens is when the threads of the atom, in this case a piece of the atom, which would be the s orbital and the p orbital, which would be part of another atom. There's no such thing as a standalone p orbital, right? They swing around in the same direction, and that's where the attachment occurs, in the high energy region. Okay, so this is what we're proposing, that's what is called ionization, or you could say that's what causes the attraction between atoms, what they call a bond. James Bond, their bond is magical because they always draw it as a stick. And you say, what is that stick? Oh, we don't know, but we always draw it and it works. Works miracles. People look at it and say, oh, okay, I see why they're attached, because it's got this James Bond, this 007 that's connecting two atoms. No, there has to be a physical reason, entity there, and that stick that they put in there is not a physical entity. You'll never find it in the standard model. They just put it in by hand. Okay, they never explain what that stick is. They say, oh, it's a bond. Bond of what? Is that a physical bond? Is it just a number? What is that? Okay, that's the issue. Okay, so here we explain electricity and magnetism. Atoms are merged one with another, and what they do, they swing these threads, not the ropes, the threads. People confuse threads with ropes. These are threads. They're being swung around. You can see the electricity flows to the right, okay? Current's going to the right, and now you see why the magnetic so-called field, right, is swinging perpendicular to the direction of the electricity, okay? And so, yeah, threads come out of the atoms, and that's what produces attraction, because if they move in the same direction as we just showed, they attach to each other and pull. Just like the two kids that were swinging their ropes around and getting interfered by the other rope. Okay, so that's it. Okay, so what else don't we have? Well, we don't have wave packets, right? And why is that important? Because you have this thing called redshift that we talked about the other day. What is the redshift? Well, the way they looked at it until today is in one way and one way only. And that's got to do with Olber's paradox. What is that? You have the sound of a car coming or a train coming towards you and goes, they squeeze it, all the waves, and so that comes in very high pitch to your ear. And when the train goes away, it goes, and why? Because now the waves, as they goes away, right? The waves allegedly get farther apart, and they get longer wavelengths, and now they don't come at the same frequency into your ear, and that's why the sound goes down. That's called Olber's paradox. So what they did, they took this sound thingy and they translated it into light. So we have Olber's paradox in light, okay? And so when they want to explain why the universe is all redshifted, they say, oh, we know it's Olber's paradox. Everything is running away from us, except for the local group. We don't know why the local group? I don't understand that. Okay, let's find out. Okay, so this is what they propose. They say, look, we have this thing called blue shifted local group, and they're blue shifted. They're all coming towards us, these galaxies, or most of them are at least. And so they say, well, those are coming towards us, and that's why they're blue shifted. On the other hand, all other galaxies out there, the farther they are, the redder they are. And you say, how can that possibly be? Well, it's got to be Olber's paradox. They're running away from us, and so they're stretching the wavelengths, right? And so we have a problem first, because the first problem we have with this is that the blue shifted ones, why don't these, why aren't they running away from us? If you have this balloon analogy, which is what they always show, and here it is, balloon analogy says that the universe is expanding, right, since the day of the Big Bang. And so everything should be red shifted out there. There should be nothing that is blue shifted at all, because Andromeda Galaxy, which is one of the biggest, nearest galaxies that we have, should be running away from us, should not be coming towards us. Why would it? If the balloon space is expanding, it should be pushing it outwards. And that's when they had to create the mechanism that, well, electromagnetism overrules gravity, and so it pulls all the local stuff closer to us. So that's the solution they gave to that. Meanwhile, all the others go with this thing that means that all the galaxies are running away from us. And they dismiss tired light. What is tired light? Tired light means that if the light from a galaxy hits something coming from a galaxy, hits something, hits a stone, hits a piece of gas or whatever out there, then it slows it down because it's going through some more dense matter, and so all this light would be hitting all these things, and they cannot imagine that, how light just hits all these gases, everything that's between us and the galaxy, and so they dismiss tired light as a possibility, and so they just stuck with Olber's paradox, and that's what they have today. And because of this, they said, well, if you pull all these galaxies which are running away from us, and you pull them back to where they were yesterday or the day before or yesteryear or last century or whatever, you go backwards in time, well, all these galaxies were closer together. And guess what? If you take them 14 billion years ago, well, they're all in a single singularity, right? A little whatever that is, an infinite whole. From which everything came out of, and that's called the Big Bang. Okay, so that's how they arrived at the Big Bang, because of this nonsense called Olber's paradox, which is wrongly applied here. Now that doesn't mean there is no redshift related to Olber's paradox. Okay, I'm just saying that's not the only mechanism that we have. We have this other one which we propose, and we propose it why? Because there's no such thing as a wave. An electromagnetic wave, a transverse wave. There's no such monster. What is that? That's just a mathematical contraption. Just yet another one, okay? Here it is, okay? Just summarizing, wave is a magnetic field. What is a field? A bunch of numbers. That's all that a field is. And what is it made out of? Made out of vectors. What is a vector? Bunch of numbers. So we have numbers on top of numbers on top of numbers. That's what a wave is. And so all those arrows that you see there inside the electromagnetic wave, the transverse wave, are just numbers. And what they do is they put these numbers in there, they represent them with arrows, and people think that they're looking at a thing when they're not. They're looking at a representation, a pictorial representation of a number. That's all there is. What you have there, those arrows are just magnitude and direction. That's it. And the worst part is when they start putting this in motion, they say, oh, the magnetic field and the whole thing, right, the whole wave moves towards the right, in this case, right, example, and they go one way. So these things, allegedly, these arrows are coming out of an atom. What's coming out of the atom? Numbers and values. That's it. That's all you're staring at. There's no such thing as an electromagnetic wave. Now, we know they oscillate after, we have this intuitive feeling that there's an oscillation of something up and down, maybe transverse with respect to the direction of motion, right? And what we're saying, what these people have been looking at all these years is a rope. They mistook it for this thing that they described mathematically, which is the wave. And this rope is simply torques in place. And now you can explain the speed of light, because torsion is the fastest thing that you can imagine. If you can imagine anything faster than torsion, please let me know and put it in the comments section, okay? There is nothing faster than a torsion, and that explains the speed of light, why light is so fast. And it also explains the inverse relation between frequency and wavelength, because little c is 300,000 kilometers per second. That's a constant, and the only way you can maintain a constant there is by raising the frequency and lowering the wavelength, or vice versa. And the only thing that can imitate that, can simulate that, is a rope configuration. That's it. There's no other thing. If you have some other idea, please let me know also on that. If you think that there's something you can imagine that can represent the inverse relation between frequency and wavelength, hey, I'd like to hear it. I'll challenge everybody on planet Earth, especially people in Cambridge and Harvard, so-called scientists, okay? Okay, so what are we proposing? We're proposing to replace the spectrum, and instead of waves, we're going to have ropes, okay? So the one on the left is the nonsense we live with today. They call them waves. And what's waving? Well, a bunch of vectors. That's it. They don't draw the vectors. They just draw this standing wave, which is absolute nonsense, because we need to know what physical entity that is. And we're saying it's on the right. It's a rope, and it's not going up and down. It's torsion, okay? It's this torquing of the wave, of the rope, okay? Okay, so that's the model we propose. You don't have to believe in it. We just explain so that you understand it, okay? You can choose the wave version if that's what you want to believe in, no problem. We have no problem with that, okay? You can believe in God if you want, or angels, we don't care. And here it is. So we replaced the wave there, the one at the bottom, with the rope. We're saying what happens is you have a rope that is tied from one atom in a galaxy to an atom here on Earth, you could say in our galaxy, in your eye. So why can't we see galaxies which are far away? Well, because they're beyond the infrared. But we have equipment out there, some satellites and probes out there that can see farther. They can see beyond the infrared range. And yeah, then when they can see that, they detect it and they say, oh, there is a galaxy over there, faint infrared light that's coming from some galaxy. And they can see it with these tools that we have. We can't see it with our eyes, but there are galaxies out there. And so what's the answer? The answer is that, there are stars in every direction that you see in the sky. We see the night sky, it's all black, and then we see only a light here, a light there. We say, oh, there's a star, there's a galaxy. We see those, right? We don't see planets, but we see the thing that gives off light, okay? And what's in between? Well, we see all this darkness. We say, well, between there, it's darkness, so there's nothing there. Well, in every little direction that you can see, possibly see in the universe with trillions and gazillions of stars and galaxies, there has to be something out there, for sure, okay? So there's not a piece of sky, night sky, in which there is not something that is shining light towards your eye. Why can you not see it? You cannot see it because if the thing is far away, it's not because it's running away from you and creates this Ober's paradox. It's because when you stretch a rope, the farther you go, the longer the links. That's why. So if you look at an atom, let's take an example. There's an atom in a galaxy that's very, very, very far away, right? And it's that atom is tied to your eye. Every atom in the universe is connected to each other. So that atom there is connected to an atom in your eye. Why can't you see that if light goes through this rope? Well, because at some point the wavelength becomes so long that you get into the red range, and longer you get into the infrared range, and so on down the line. At some point, the rope probably is not even a rope. It's just probably a long link, okay? So that's why you can't see that star there. But the star is there. It's an atom of that star is connected to an atom of your eye. You cannot see it because the torsion is not reaching your eye. We got that? Okay, that's the introduction. There are no particles such as dark matter particles. There are no quarks. All this is mathematical gibberish, okay, that they created because they had no explanation for how this universe works. And the punchline is they always say, we don't understand quantum mechanics. Anyone who understands quantum mechanics, who was it, Bohr? Niels Bohr said, anyone who says he understood quantum mechanics is crazy. Yeah, nobody can understand it. Okay, and you cannot understand it because they have not made sense of the math. They cannot translate the math into physics, which is what we all would understand. I mean, if you show me the movie of the mechanism, we all understand it. They can't do that with the math of quantum mechanics. That's why all the math from quantum mechanics, as well as general relativity and string theory, is absolute garbage. We've lost 100 years developing math for, dark unicorns, black leprechauns? Is that what we... Okay, let's move on. Okay, let's see if we can make some sense out of some of these things. Well, it only gets worse. Let me show you. If we would have stopped there, that wouldn't have been maybe so bad, but it just gets worse every year, and it's a monster now. You've probably seen the standard model. It looks something like this. Let me show you. Here it is. That's a standard model. Okay, those are the 16 particles plus one, the Higgs, we'll call it 17. We don't have the graviton. I'm sorry, I can't post that there because they haven't discovered it yet. Discovered, they always discover these things. Okay, so we have these 17 particles. We're done, right? Let's all go home, drink champagne. It doesn't work that way. It doesn't stop here. I wish they would have stopped here, but they created more and more particles. They discovered more particles, okay? So here, let's look at all the particles that they discovered. Here we have the, well, you've seen the quantum atom, right? Here it is. That's what it looks like, right? And it's made out of those particles of the Standard Model. You have the electron there, the blue one going around. You have the proton in the center, not drawn to scale, by the way. And you have the three quarks that have these gluons that are pulling them together. And obviously, they're always shown as bed springs, right? That expand and contract, okay? So that shows you one of the reasons that the quarks don't fly away. The other reason is that they're in this red ball called this enclosure called a proton. So I don't know what that red stuff is. They just put a ball around these three balls and they say, look, that's one of the reasons the quarks don't fly out. And the other one is they're held together by these gluon bed springs. Okay, so everybody looks at it and says, oh, I understand it. Yeah, but that's just math. Okay, that's nothing to do with physics. And they have this little electron going around, and the question is, why does it fall, if it's negative, why doesn't it fall to the positive proton? Or why doesn't it spontaneously fly away from the atom? And they never explained that, either one, okay? So, but this is our atom, and that's what everybody illustrates, and then they tell you, well, that's not our real atom. And the only time they say that it's not the real atom is to show you that it doesn't go like in orbit, like Pluto or Jupiter or whatever. It jumps around, so they don't know where the electron is, but it could be in this region. And that's the only difference between the Bohr model. The Bohr model was a circular orbit, so to say, right? And these people are saying something different. They're saying, oh, we don't have the Bohr model, like if they had a different model altogether. Not at all. What they say is that the electron bead is jumping around within a certain region. Okay? And when it does, when it jumps back and forth, it emits waves, electromagnetic waves, which are a bunch of fields, which are a bunch of vectors. Okay, that's what they're throwing at your face. They're throwing vectors at your face, bunch of numbers. Okay, here you have one specific atom, illustrated not by me. I just want you to see that this is what they illustrate, okay? This is lithium. It's number 3 on the Mendeleev chart, okay? And it's got 3 protons, 3 neutrons, and 3 electrons running around, okay? And you have these 2 circles. Why? Because these are the s orbitals, okay? You can have at most 2 in the S1 orbital. There you have it, okay? And you have the other one running around, okay? And there you have it. That's the image they have of the lithium atom. And again, you're not supposed to look at this as very circular orbits. You can think of them as the electrons jumping around. But that is what they illustrate. That is the atom. Again, why doesn't the electron, negative electron, fall to the positive proton? Why doesn't the electron spontaneously fly away? No answer to that. You'll never get one. Let's just move on. That's what they say. Don't ask those questions. Go ask the philosophers. They know. And the philosophers receive their cues from these bozos. Okay, so is that the end of it? No, now we get into the heavy stuff. And now, at this point, I'm going to ask you to drink a beer or a good shot of whiskey, okay? Because this is going to get very strange now, okay? Here's the muonic atom. This is a muon atom, okay? What is a muonic atom? Well, there you have it, okay? This is what they show you. This is what they discovered. I'm sorry, that's the correct word. Muonium, discovered in 1960. Exotic atom, okay? Atom in which subatomic particle was replaced by what? Other particle. In this case, the muonium. Exotic atom made up of an anti-muon and an electron. Okay, so there you have it. Why the anti-muon? Because it's a positive one, and so you have to have the negative electron running around a positive muon. You got that? So we don't have a proton in there. What we have is a positive muon. So whenever they ask you, look, what does the hydrogen atom look like? Well, it all depends. If you do replace the proton with a muon, you're going to have a muonic atom. That's what you're going to get. And I've never seen that in the in the table of the elements, right? Or in the Standard Model, for that matter, as a unit, as a particle, because after all, the atom is a particle, right? No, they just say, we're going to break all these into pieces and talk about the little pieces in the Standard Model. And there you have it. It's anti-muon, positive muon, right? Anti-muon, opposite charge, plus a plus 1, because they're talking about charges. 1.6 times 10 to the minus 19 coulombs, that's all they're talking about, numbers, values, okay? But equal mass and spin. So instead of having a negative electron, you have kind of like a positive electron in there, and that's called the anti-muon, okay? Okay, so now you know what that looks like and what that is, and this is what these people present out there, okay? Believe it or not. Okay, here you have, let me get this one out of there. Here you have the another version of this. There you have it. You have the ordinary atom, and then you have the muonic atom. And there's one place that says muons replace the electrons in atoms. Okay, and so what you have is a muonic cloud surrounding the normal sized nucleus, and they are 200 times smaller than the electron cloud around the normal atoms. So there you have a muon that replaces the electron, runs around the proton in this case, right? Because they have all these versions of the muonic atom. And because it's so massive, the orbit, the circular orbit, which is not a circular orbit, is closer to the proton. That's all they're saying, okay? So they have all these versions. They have the electron running around the muon. They have the muon running around the proton. I hope you're following all this stuff, okay? Because they had to answer questions, and they said, how do we explain this phenomenon that we can't see, observe, right? They always observe, but they can't see it. And how do we explain that? Oh, I know. We'll put a muon in there and replace the proton or the electron. We'll have the muon running around the proton. And so they make all this stuff up. It's all made up. None of it is real. It's just nonsense. And just in case you thought saw the end of it, here's the pionic helium. Okay, this is another atom, and they don't have a muon; they have a pion. What's a pion? Well, if you know your relativity and your quantum, both of them, you have these pions which travel at close to the speed of light. They break up, they decay into muons, which later on decay into electrons and then fall to Earth. And then you have also the time dilation thing in there, okay? No, we're not going to go into the little stuff there, little details. But here you have a pionic helium. And instead of a muon, you have a pion, okay? But it has a very short life. But while it has a life, electron protects it. As you can see there, negative pion in a circular orbit with diameter 100 picometers does not touch the nucleus, okay? Electron protects pion during collisions with other atoms. How nice of the electron. Yeah, they had to create all this nonsense because they cannot explain anything that they observe. They observe it, okay? They discovered it, but they cannot explain it, so this is how they explain it. They invent this stuff. They invent names for inexistent particles. That's what they're doing. Here you have the decay, proton and neutron. We explained earlier, you have two ups and one down. They all let me know. They reconnected me. I hope I'm still on. Let me know. YouTube didn't like what I was saying, I guess. So they disconnected me. Thank you. Okay, anyways, we have proton and neutron. Very straightforward, right? Okay, neutron doesn't have charge because it's got 2 negative 1/3 plus a 2/3 up quark, 0. And the other guy has 2 2/3 minus 1/3, that's 1. It's got 1 charge. We're done. It's very simple stuff, right? All math. Does this really exist in reality, or is this just a mathematical footwork, fancy footwork to explain the unexplainable with particles? Okay, so it turns out that the proton, and as well the neutron, by the way, but the proton is not made of 3 quarks. I'm sorry to tell you that. I wish I could tell you otherwise, but it turns out it's got gazillions of quark, anti-quark pairs that constantly annihilate each other. They turn into empty space, I think. I don't know. What is annihilation? Well, you would think it's they annihilate, they disappear. Like Merlin, the magician, he makes himself disappear and he turns into nothing. What's nothing? Space. What's space? Vacuum. No matter. You would think that's what annihilation means. But they say that these things are going on, and there's always more positive quarks in the in the proton than there's 2 against 1 always, right? In a proton, there's always 2 down quarks against 1 up quark in the neutron, right? But there's all this activity going on inside the proton, inside the neutron, where all these quark-anti-quark pairs constantly annihilate each other. So the proton and the neutron are just not made of 3 quarks. They're made of gazillions, infinite number of quarks that are constantly coming in and out of existence. And the question is, when they come into existence, how many quarks does the proton, the neutron, have at that specific moment in time? And that's for you to take as homework. Figure it out, okay? But here it is, just in case this is not me. This is what I get out there, okay? It says, you may have heard that a proton is made of 3 quarks. This is a lie, a white lie, but a big one, okay? In fact, there are zillions of gluons, antiquarks, and quarks in a proton, not to mention the neutron, right? The standard shorthand, the proton is made from 2 up quarks and 1 down quark, is really a statement that the proton has 2 more up quarks than 1 antiquark, and 1 more down quark than down quark, antiquarks. To make the glib shorthand correct, you need to add the phrase plus zillions of gluons and zillions of quark-antiquark pairs. Without this phrase, one's view of the proton is so simplistic that it is not possible to understand the LHC at all. And you can see all the gazillions of up quarks and down quarks there, and antiquarks and whatever quarks, okay? They put them in there, but again, there's got to be a ratio of 2 to 1 for proton and 1 to 2 for the neutron, okay? So, a proton is made of gazillions of quark-antiquark pairs that constantly annihilate each other, okay? So let's make sure you understand that. The only question I've got is, when the things come into existence, all these quark-antiquark pairs, how many do we have? Because, they are all annihilated, no problem. They don't exist for all practical purposes. But when they come into existence for that brief gazillions of a second, then how many quarks does a proton have? And they have to have gazillions. I mean, that's the way it is. And here, just in case you say, Bill, you're pulling at straws. No, here's a girl, dubbed her voice, right? But you'll hear from her mouth, and she sells this on the internet, okay? And she's a so-called physicist, okay? So listen to her. She'll tell it to you in her own words, okay? Here it goes. Listen carefully.
So protons are made out of 3 quarks. That's the first lie you're told. The proton could have an additional up quark, anti-up quark pair, and it could have other types of quarks, pairs of strange quarks and anti-strange quarks, charm quarks and anti-charm quarks. In fact, the proton likely has tons of quark-anti-quark pairs. Quark-anti-quark pairs pop in and out of existence. The quarks are held together by the strong force, which is carried by particles called gluons. So inside the proton, there are zillions of gluons and quarks all zooming around close to the speed of light and colliding and annihilating, and new ones are forming, and it's a crazy raging party, such as the quantum world in a proton.
Did I lie? Yeah, that's what they're saying. These people are saying there's all these anti-quarks and quarks and quarky people inside these atoms, protons really, neutrons, and they constantly annihilate each other, and you can see that she puts them all in there and just starts smashing them with a hammer, showing you that they annihilate each other. But when they annihilate, I can still see the M&M there. So she's got a lot of chocolate on that table, right? Okay, did we stop there? No, we go with the Tao. What's the Tao? Well, you heard the Tao of physics. Okay, the Tao of physics, there it is. Tao, an elementary particle similar to the electron with negative electric charge and a spin of half. Okay, great. A Tau can be thought of as a much heavier version of the electron, but much more highly penetrating than electrons. They did not detect the Tau directly, but rather, what? Discovered. Okay, now we have a discovery, okay? Keep those words in mind. Anomalous events of the form E, going to an E muon there, okay? At least two undetected particles for which we have no conventional explanation. So they had to find an explanation for this math, right? And that's when they created the Tau. The need for at least two undetected particles was shown by the inability to conserve energy and momentum with only one. However, no other muons, electrons, photons, or hadrons were detected. It was proposed that this event was the production and subsequent decay of what? A new particle pair. And there you see the two taus, the plus tau and the negative tau, which they had to put in there by hand. Okay? And this comes from the Wikipedia, the peer-reviewed encyclopedia, which never lies. Okay? So that's how we got the tau in there. Does the Tau exist? Well, it does now. In the minds of the mathematicians, the mathematical quantum guys, mechanics. Okay, once again here we have good old Anderson and his suppositron, okay, and that was the trace that we say was a whack by maybe a thread or a bunch of threads, but he thought it was a particle, a trace, okay, and so the question is, what caused that? Well, he called it the positron, which I call the suppositron, okay. So now you know what a positron is, a little particle that goes to the left instead of to the right like the electron would have. Okay, that's what it is. What did they do with this? Well, they created the positronium. Okay, keep that in mind. This is a very important scientific stuff, okay? The positronium, okay, here it is, the positronium. What is that? It's a positron with an electron. They're running around each other, you know, playing ring around the rosies. Okay, positronium, system consisting of an electron and its antiparticle, a positron, okay? Bound together, bound by what? By, what are those, contrails? Like airplanes, you know, they leave the contrail behind. Mighty Mouse, you know, I have this cartoon where the, what is it, the little sheep walk back and forth on the contrail, and that's more or less what they have there. The binding, the bound means that they're turning an itinerary into a physical object, in this case a hula hoop, okay? An electron and its antiparticle, a positron bound together into an exotic atom, specifically what? An onium, okay? One of these oniums. Unlike hydrogen, the system has no protons. So we have a hydrogen atom without a proton. Great. What do we put instead? A positron. The system is unstable. Yeah, because the two particles, they annihilate each other, whatever that means, right? And when they annihilate, they throw a bunch of energy, whatever that is, which is a bunch of waves that have frequency and wavelength, whatever that is, because all that is numbers. So far we have no physics. All we have is numbers, math, irrelevant math, because descriptions are not explanations, and we need an explanation for what's happening in the quantum world, and they have no idea because they cannot explain it with the particle hypothesis. That's what's failing here. You cannot explain any of these things with particles. That's the key issue. Okay, so there says the system unstable, the two particles annihilate, and to predominantly produce 2 or 3 gamma rays, whatever that is. A ray is a concept, right? It's a bunch of waves. They wave the gamma ray bye-bye, depending on the relative spin states. Okay, good. So that's a positronium, okay? Now you know, okay? Very important stuff. Please memorize it for the test on Friday. And not to be confused with a protonium. Okay, here we have a protonium, okay? Protonium, what is that? 2 protons. But we have a negative proton. You know, it was always positive, but they had to create the negative proton to explain some nonsense out there. It's an onium, a bound state. Bound by what? Oh, by a hula hoop, whatever that hula hoop is, just in case they put a cloud over it to show you, you know, that why the proton can't run away, right? And a bound state of a particle and its antiparticle. Okay, and so we have protonium, also known as antiprotonic hydrogen. A type of exotic atom in which a proton and an antiproton are bound to each other. Talk about marriage. Here you have a positive and a negative. I wonder which is the female here, yeah? Yeah, so they created a protonium, not to be confused with a positronium, okay? Please do not confuse these important scientific concepts. Okay, here we have, you thought we stopped there. No, we have the quarkonium. We have the quarkonium, okay? It looks something like that. Doesn't that look nice? Quarkonium. The blue and orange balls represent charm and anti-charm quarks. Charm being a property of quarks, I guess, with gluons connecting all of them. What does a gluon look like? Oh yeah, it was a bed springs. I forgot about that, okay? Let's show that again. Okay, this is what a bed spring is. Okay, it looks like, if I can see it here. Where'd it go? That's what a gluon looks like, bed spring, okay? And when people say, "Oh, you're making fun of these great scientists or whatever," that's what they're illustrating. So I illustrate it as well. And I don't see bed springs in the standard model. I never saw a bed spring. I always see little balls. So how this quantum gluon turns into a bed spring, I don't know. But they have to put a bed spring to explain why the quarks don't fly apart. That's why they put those bed springs. There's a reason for that, okay? And again, they're trying to turn their math, right, which they just create to fit the facts, and then they turn that into a physical entity saying, oh, it's a bed spring. That's how they illustrate it. And when you question that, they say, Bell, you're criticizing my analogy, just an analogy. Analogy of what? They're putting a bed spring, and we can see why the quarks don't fly apart, because they have an elongated thing that holds them together. So it's not, is that what they're saying, that there's a bed spring there? And they say, well, you're taking it too literally. What's a quarkonium? A flavorless. So don't ever taste that because it's flavorless. Meson, comprised of a heavy quark and its own antiquark, making it both a neutral particle and its own antiparticle. Okay, so now you know. The name quarkonium is analogous to positronium. Okay, do not confuse them. The bound state of an electron and an anti-electron, and the particles are short-lived due to matter-antimatter annihilation. What do they produce? I guess gamma rays or some kind of ray, X-rays. I don't know. So yeah, what these people talk is nonsense. They say, look, they annihilate, but annihilate doesn't mean they turn into nothing, which is what annihilation means. No, they turn into energy, which is a mathematical concept. And so what is energy? Well, people say, well, we transfer energy, and that means you're transferring a physical object, a cloud of dust or whatever, however you can imagine that. It means energy is not nothing. That's what they're telling you. And so annihilation into what? Annihilation just means that two pieces of matter, a negative and a positive matter, ball or whatever, turn into smoke of some kind. That's what they're saying. That's annihilation. They cannot explain it because they're talking about numbers. That's why they cannot explain it. They cannot turn this into physics at all. Okay, but if you thought you saw the last of it, here it is. Hey, here we have the double charm tetraquark. Not to be confused with a tetraquark or with a quarkonium. Okay, we have the double charm tetraquark. What is that? Well, you have a T plus CC. You see two C's there. And you have also the CCUD. The U is the upper quark, the D is the down quark, and the two C's are charms. Okay? So we have the charms and the other quarks, these up and down quarks. A type of long-lived tetraquark discovered in 2021. Hey, this is a new discovery, new Nobel Prize coming down the road, okay, at the Large Hadron Collider. Okay, it contains 4 quarks, 2 charm quarks, and an anti-up and an anti-down quark. Okay, so these are anti. Okay, not these are not straightforward ups and downs. These are anti-ups and anti-downs. Anti-down is an up, I think, and an anti-up is an anti-down is an up, right? I guess one is the opposite of the other. They've got me confused here, you know. It contains 4 quarks and these 2 charm quarks and an anti-up and anti-down quark. It has a theoretical computed mass, I have to put a mass in there, of so-and-so, what? Mega electron volts. I thought that was energy. Yeah, because mass is energy. Remember that, okay? So that's why they put all this, they talk about mass and they're really illustrating energy, electron volts, okay? Okay, so if you thought you saw less of it, okay, here we have the charmonium. Charmonium. And we have different kinds here. We have the charmonium, the bottomonium, and the toponium, okay? And what are these? Okay, we have a flavor neutral meson consisting of a charm quark and a charm antiquark. What's a bottomonium? Bottom quark and its antiparticle. And then the toponium is a top quark, right? Hypothetical. This one's hypothetical. The others are real, proven, discovered. This one's just hypothetical. Form of a quarkonium. That is a flavorless meson. Don't recommend that you taste it, okay? Formed by a top quark and a top antiquark, okay? So how's that for particles, okay? Yeah. All this will be on the test on Friday, so I hope you memorize all this stuff, okay? It's very important scientific stuff. And if you thought you saw the last over here, we have the strangeonium. The strangeonium, okay? What's a strangeonium? Well, it's all that nonsense that you see there. Always mediated by the gluon bed springs. Do not forget the gluon bed springs. They have to be, stretched and compressed constantly. And one fellow writes, the ground state masses of the pure SS states are evaluated. Further, the Reggie slopes are extracted for kaons and strangeonium to obtain the orbitally excited state masses in the JM2 plane. Whatever all that nonsense means. These people write papers on this garbage. They call them the strangeonium. They have to have something to do, and so this is what they study on. And what are they? If you look at the paper, it's just a bunch of numbers, equations, and you say, well, Bill, you don't understand all those equations. Look, I don't want to understand it. Even if I did, I don't want to understand it because that's not physics. Math is not the language of physics, and this proves it. The fact that you cannot represent all this math in physical terms with images, which is the language of physics. Images. You have to be able to illustrate things. You have a theory, you have a mechanism, you better be able to illustrate it. They cannot illustrate a single mechanism in quantum mechanics or in general relativity or in string theory. Now, isn't that kind of coincidental? We don't have a picture of the big, we don't have a picture of the small. Why? Because all they have is math equations, and they cannot translate those equations into images. That's the whole problem. Okay, because you can't translate an equation into physics. Maybe you can put an equation for a chair. Would that give you an idea? Would it give the idea to extraterrestrial? A Klingon comes to visit us, and we give him an equation. He says, what's that? That's a chair. What is that? It's an equation that represents the chair. We represent it with a chair because it's the equation of a chair. Yeah, sure. That's the problem. These people cannot do that. And so if you thought you saw everything, now we have the, oh my God, particle. Here it is. Oh my God, particle in ultra-high energy cosmic ray, what? Detected on October 15, 1991. It is the highest energy cosmic ray. What's a ray? A concept. Okay, it's a wave. What's a wave? Bunch of fields. What's a field? Bunch of vectors. So all they have is numbers. Ever observed? Oh, they observed it, like, with two eyes? No, observe is a misleading term. They never observed anything. They're blind. That's what they are. But they use the word observe and detected and discovered, and that drives home the point that they've proven it. That's what they're telling you. We proved it. Believe it. And it's going to be on the test. So if you don't pass the test, you don't get your degree. That's how simple it is. Estimated at so many electron volts, 10 to the 20th. The particle's energy called into question prevailing theories about the origin and propagation of cosmic rays. It is not known what kind of particle it was, but most cosmic rays are what? Protons. Its speed was close to the speed of light. So we have a proton traveling almost the speed of light, right? Or something big like a proton, I guess, right? Due to special relativity, now here comes relativity into the picture, the relativistic time dilation experienced by a proton traveling at this. I hope I'm still on. Let me know. They reconnected me. Please let me know if I'm still on. They said they reconnected me, so I must have been cut off for maybe a minute or so. Thank you. Jesus Christ. I think it's censorship. Okay, and why not the quasis? We have some quasis here, okay? Listen to the quasis. Here we have the polaritons. What is that? Bosonic quasi-particles resulting from strong coupling of electromagnetic waves. What are waves? Again, numbers, that's all they are. Photon with an electric or magnetic dipole carrying excitation state of solid or liquid matter such as phonon, plasmon, or exciton. What are these things? Well, we have the photon, the phonon, a collective excitation, a periodic elastic arrangement of atoms or molecules. In other words, what they have is this so-called phonon, and what is it? They have all these particles and they make them vibrate, and they call the whole shebang a phonon. They treat it as a single particle because they call these things particles. Then you have the plasmon. Okay, what is that? A quantum of plasma oscillation. Just as light, an optical oscillation consists of photons, which is really not a bunch of waves, meaning fields, meaning vectors, right? Numbers. The plasma oscillation consists of what? Plasmons. So now you know, okay? And what's an exciton? A bound state. Bound? What is bound by? A little string of an electron and an electron hole, which are attracted to each other by the electrostatic Coulomb force resulting from their opposite charges. Now, I've shown this in the past, but here it is again. You saw the, the 16 square puzzles, okay, here it is. Okay, let's something like that. The little square there moves to an empty space and leaves behind a hole. So if you look at the white little squares as electrons, when they move, they leave a hole behind. And that's the notion they have for these excitons, okay? So just so you know, this is what I worked with at AMD when I was an engineer. And it says a bound state, it says it is an electrically neutral quasi-particle, Quasimodo, regarded as an elementary excitation transporting what? Energy. It transports energy, okay, on its back without transporting net electric charge. So you can either transport charge or energy, right, but not both, okay? So whenever you transport charge, let me know. Whenever you transport energy, please let me know what you are transporting. And the electron hole, what is that? Another quasi-particle denoting the lack of an electron. So you have a hole, which is the lack of an electron. When it has an electron, it's not a hole. See how it is? How easy it is? Quasi-particle, a concept, I like that, a concept, used to describe a collective behavior of a group of particles that can be treated as if they were what? A single particle. So they invent names upon names for irrational concepts, which are based on more irrational concepts. Just one turtle on top of another underneath a flat earth. That's what it is. And this is what they put out there to the public as law, as truth, as proof. And this is what these people have to study from here on, from decade to decade, from generation to generation, if they want to get a math phys degree. Okay, thought we finished there. Now let's get to the real good ones. And we have the dark photon. Dark photon, I like this one. We don't have a light photon, this is a dark one, okay? What is that? A dark photon, a hypothetical. It's hypothetical for now, right? It'll be truth tomorrow. Hidden sector particle proposed as a force carrier similar to the photon of electromagnetism, but potentially connected to dark matter. So this is how some guys are going to try to explain dark matter with this dark photon, okay? What is this thing? Well, dark matter, right? An invisible, right? Always invisible, and hypothetical form of matter. It's not hypothetical because they gave them a Nobel Prize for this. 1998 discovered, right? 2008 Nobel Prize. That's not hypothetical anymore. When people give Nobel Prizes out, it becomes a theory at least, if not a proof, right? And they're still trying to prove it, but it is a theory already. An invisible hypothetical form of matter that does not interact with light or other electromagnetic radiation. So it's got no charge. It only has mass, which is the mass necessary to be around galaxies so that the galaxy rotation problem can be explained, meaning we sprinkled masses here and there, and the equation says so. We put a lot of mass, and that explains why the stars on the outside travel faster than the ones on the inside. Very simple. It's just bunch of math. Okay, so hopefully we cover that base, right? And the punchline on all this is that, you heard of false vacuum and the vacuum that they use in quantum mechanics. Well, they say they never have total vacuum. It's like they have this levels of vacuum. That's all they can understand. That because that's what they have for in their chambers, right, where they do their tests. But they say nature abhors a vacuum. This comes from all the way to Aristotle, right? So space contains ultra-low levels of particle densities, right? There's different density constituting a near-perfect vacuum. Near-perfect, not quite total vacuum. What do I mean by that? Well, let's get that first. If you have a vacuum chamber, right, and it's full of garbage in there, fine, no problem. Now you pull particles out, okay? You pump them out, cryo pump, whatever you use, okay? You pull them out, and now it becomes emptier and emptier and emptier of particles, right? So far so good. What does it leave behind? What do we have more of if we have less particles? What is there more of? Well, we have more of empty space, which is what distinguishes one particle from another. That's what you have in there. So what is that dark stuff, that black stuff that's between the particles that there's more of now that you remove the particles? You got to define that thing. And they say, well, space is never completely empty. Nature abhors a vacuum. What do you mean by that? If you're pulling particles out, what's being left behind? What do you call that? How do you define that? How do you, what is that? And that's called space, empty space. But see, they always say that vacuum always has particles in it. And that can't be, because if you pull particles out of the system, what remains behind is empty space, and that's what you got to define. But they never did. They just said there's different levels of vacuum. And that's the big problem we have here, that they have all these irrational definitions, irrational notions, and they get away with murder. It says the mathematicians I put in there, often discuss ideal test results that would result in a perfect vacuum, which they sometimes simply call vacuum or free space, right? But they don't say that vacuum and free space really exist. They just mention it like saying, well, that's a region free of particles, right? And use the term partial vacuum to refer to an actual imperfect vacuum, as one might have in a laboratory or in space. In engineering and applied physics, on the other hand, vacuum refers to any space in which the pressure is considerably lower than atmospheric pressure. The strictest criterion to define a vacuum is a region of space and time where all the components of the stress energy tensors are zero. That's the strict definition, but they don't use that, right? This means that this region is devoid of energy and momentum, meaning particles, right? And by consequence, it must be empty of particles and other physical fields, such as electromagnetism, that contain energy and momentum. So this is what they say is a total vacuum, whatever that is, because they never defined it, because they just say it's free of particles. That's what vacuum is. So what do we have behind? What is that free of, that region that's free of particles? What do we call that? Don't we call it space? And they say no, because any bit of space has particles in it, even though they say that you can pull out particles from that space, and there's fewer particles in that given region. So what is left behind? What is that black stuff that separates particles? They never answer that question. They never define what space is. That's the issue. And then, just in case they contradict themselves, here it is. They created the local void. Is surrounded uniformly by matter in all directions, except for one sector in which there is nothing. There's nothing there. Whatever that means, whatever nothing is. Which has the effect of taking more matter away from that sector. Okay? So there's a region in space, they call it the local void, which is usually between galaxies. That region, they say there's nothing, whatever nothing is. I thought that was called space, right? Cosmic voids, also known as dark space, are vast spaces between filaments, the largest scale structures in the universe, which contain very few or no galaxies. or matter or gases or whatever, atoms, right? Although even the emptiest regions of voids contain more than approximately 15% of the average matter density of the universe. The voids look almost empty to an observer, almost empty. So they never end up with emptiness at all. They always have to put some particle in there. Why? Because they want to do measurements. What they want to do is some experiment, or they go to the lab and they create a vacuum. But they say, well, there's always particles in there. Yeah, but when you pull particles out, you left something which is increasing in volume, which is called empty space, and you need to define the word space. Otherwise, you don't know what the hell you're talking about. Okay? Okay, so what are our conclusions today? Here it is, summary. Quantum mechanics is a theory that predicts, you gotta predict, that there is an indivisible elementary fundamental particle that comprises everything else. If you chop the particle and smash them, collide them, whatever you want to do with them, I don't care. You collide them, you create more particles. Now you take that other little particle, you collide that one, and collide that one, and collide that one. At some point, you had better end up with, you can't peel the onion and end up with nothing. You end up with a particle at the end of the yellow brick road. You have to have a particle there. Okay? So I don't care how many times you smash it, conceptually, right? We don't need to go to the accelerator, the Large Hadron Collider, to do this. We can just mentally say, look, if we collide, at some point you end up with one particle that makes up all the others to some degree. Okay? That's the only elementary fundamental particle. All others have better be made of that little particle. And so the electron has to be made of particles, but they say it's a fundamental elementary particle. What do you mean by that? Well, I mean by that it's not made of smaller parts. Okay, how do you know that? We try to smash it, and we can't smash it because we don't have the energy to smash it, and therefore we don't know what it's made of. But that's a wrong reasoning. The reasoning is, if we were to mentally smash the electron, what would it be made of? Charlies? Johnnies? Peters? I mean, what's it made of? And there's got to be one at the end of the yellow brick road that comprises all the other ones that make up, the electron. So that's the issue. Quantum mechanics is a particle theory. If it's a particle theory, there has to be a particle at the end of the yellow brick road. You can't not go smashing all the way to the end of the road and not find a particle. You cannot find nothing. You cannot say the particle is made of nothing. That is irrational. So quantum mechanics predicts, the theory requires, demands that there be a particle at the end of the yellow brick road after all the smashing, all the collisions, all that stuff, right? Experiments only serve to collide particles incessantly. And that's good stuff, see, because it gives them job security, right? Any trace in an accelerator bubble chamber is treated as a trajectory of a discrete particle and imaged as such by computers. So they don't really have a particle. They say, we think it's a particle. We assume it's a particle, but they put it out there as, we've proven, we detected, we discovered the muon, the pion, the quark, or whatever, gluon. And then mathematical mechanics, we can call them quantum mechanics, now I call them mathematical mechanics, have job security until the end of time, just working on naming alleged particles that they discover in each generation. Yeah, if you want a degree, if you want to have a job at the Large Hadron Collider or at the NASA or whatever, you're going to have to bow down to the math. And what's the math? Well, math, they can do equations. They do tons of those on irrelevant stuff. They do them on, again, on dark unicorns and black leprechauns. So, okay, great. So what? So they have all these equations. What are they good for? What do we need them for? And the answer is give them job security. So if you memorize the catechism, you get a job at NASA, and Large Hadron Collider, LHC, whatever, and you get a job. You got job security to do what more equations on more nonsense that doesn't exist. And that's known as mathematical physics. I'll see you next week. Bye-bye.